too many details because it's also quite technical. And therefore, I have a relatively long motivation part that is a bit more general about microfluidics. So the idea is here that we want to look at the formation of pairs of soft particles in inertial microfluidics, a numerical point of view, of course. And you might remember the last presentation yesterday by Ottman, who talked about inertial microfluidics with rigid particles. And today's talk it could be seen as a continuation of that presentation yesterday. So first of all, I would like to acknowledge Ben, who is a postdoc with me, and he did all the work. So everything that you see, all the plots and so on, that is Ben's work. I would also like to thank Christian Schaaf and Holger Stark at the TU Berlin for discussions, because our project is also based to some extent on what they have done before. Then Prosenjit Bakshi, who has done some simulations of capsules in inertial flows, and we had a discussion about this work. Erik Essmann, he is another postdoc in my group, and all the simulations were run on the Cirrus supercomputer at the Edinburgh Parallel Computing Center. Also, I would like to acknowledge, do you see the mouse, by the way?
Yes, we see the mouse.
Okay, that's great, thank you. I would like to acknowledge funding from the European Research Council for the starting grant. Ben is paid from that one. And also I would like to thank my research group and the Cirrus project, which is the ERC funded project. Okay, what do I want to talk about today? First of all, motivation. I promise you it will be hopefully entertaining and probably half of my talk. Then very, very quickly, an overview of the physical and numerical model, followed by some simulation results, and of course, a bit of an outlook. So first of all, you might have seen a device like this, where you have a number of cells coming in a microfluidic channel in a water solution, and you encapsulate them in an oil environment, which means you get a water and oil droplet. You keep the cells alive inside, and you can do something with these cells later on. And I'm pretty sure that all of you have heard recently about PCR and so on, very topical, COVID and other diseases. What you can do with these systems is you can isolate single cells in microenvironments where the cells are encapsulated and protected. You can feed them, you can manipulate them, you can do all kinds of stuff. And later on, you can analyze what is happening inside. For example, you look at the genetics, you can prod them with drugs and see what the responses of individual cells and so on. And let's look at an experiment. And I would like to, it's about 40 seconds, this video. And I would like to ask you while you watch it, if you were the experimentalist running this, what kind of, why would you be unhappy with this experiment? So let me play the video and watch how the cells are encapsulated. So you can see cells are coming in the water stream, there's an oil stream, you have flow focusing, and you have droplets with cells inside. And later on, you get a suspension of these droplets. Of course, you also have surfactants involved, because otherwise there would be a lot of coalescence, which you want to avoid, obviously. And this is how it looks like. And then what you can do, you can post-process, or you can do something with these droplets that have cells inside. And now the question is, what is not so good about the situation? You can see already there is one droplet that has actually two cells inside. And you have quite a large number of droplets with absolutely no cells inside. So if I go to the next slide, this is what you see. Although you can make very, very beautiful droplets these days, which are essentially monodisperse. I think they have maybe a 1% size variation. That is absolutely possible these days. But what is a challenge is to end up with exactly one cell in one droplet. And the reason behind that is that normally you have the Poisson distribution, Poisson statistics, that is telling you how many cells you will have in a droplet. What we really want to have is we want to have a peak at the value 1 cell per droplet, and essentially nothing at 0, which means you don't want to have empty droplets because it's just a waste. And also you don't want to have more than 1 cell in a single droplet, because if you have more than 1 cell and they have different behaviors and you analyze what's happening inside one droplet, you can never be sure what is coming from which cell. So what can we do about that? What can we do to increase the peak at 1 cell per droplet and suppress everything else? There's also another application in microfluidics that you might have seen, flow cytometry and fluorescence activated cell sorting, for example. So let's say you have an inlet, you have different types of particles or cells, could be, for example, cancer cells mixed with red blood cells or something like that. And some of these cells are stained with a fluorescent dye, for example. Then what happens, you have a device with laser light shining, you have detectors that see whether a cell is actually fluorescent or not. And then you have some kind of downstream trigger that pushes cells to the left or to the right in a simple way. And if that works, then you get 2 different containers with cells. For example, the cells you are interested in and the cells you want to discard. Okay. Now let me show a video here. This is with, you can see here that 1 cell is currently in the laser beam and it's fluorescing. And the trigger mechanism to push the cell away, it's actually not a cell, it's a particle. These are rigid beads. The mechanism is a surface acoustic wave. The particles, let me just play it, they come from the right. You see some of them are showing fluorescence, and those are then pushed by an acoustic wave a bit more to the right in direction of travel, and these particles leave in another outlet. I find this quite impressive because this is very fast. You can process several thousand cells or particles per second in these devices. It is extremely fast. Now, the problem is, if I go back to this slide here, you can imagine if the cells or particles are too far away, if the spacing is very large, then of course you're wasting a lot of throughput. You need a lot of liquid, but you have hardly any particles to process. And if they are too close, then you can sometimes not distinguish between them. So what you would like to have, or you even trigger an event and you get undesired particles in the desired sample, for example. So what you really want to have is you want to have an equal spacing between these cells as much as possible. And you would like to have the same for the cell encapsulation that I showed you at the beginning. And the question is really how to beat the Poisson statistics. What can we do about that? Now, inertial microfluidics can help. And some of you have seen the presentation yesterday in the afternoon. What is inertial microfluidics? Inertial microfluidics is basically microfluidics with flow that is so fast that inertia cannot be neglected. And typically you have Reynolds number between 10 and maybe 1000 in a channel. It depends on the application, what you want to do. And there are various applications of inertial microfluidics. The research field is growing very quickly. There is a lot happening. What you might be aware of is the so-called radial migration or lateral migration of particles in flow. Ottman talked about that yesterday in his very nice presentation. So if you have a straight channel, and everything that follows in this talk is in a straight channel. If you have a straight channel and you have, let's say, rigid beads, rigid particles, in the Stokes limit, they will not migrate. They will just stay where they are. Of course, you might have fluctuations because the beads encounter other beads and you have hydrodynamic interactions. But if you have a very dilute suspension, then the beads will essentially keep their lateral position. If you increase Reynolds number, then, and this was observed in the 60s by Segre and Silberberg, you can see that these beads, they arrange on an annulus, if you have a circular cross-section, about 60% of the radius of the tube. And that depends on the Reynolds number as well. However, something even more interesting is happening in inertial microfluidics if the particle concentration is sufficiently high and not too high. If it is in the right range of concentrations, then particles see each other and they can form trains and staggered trains, as you can see it here. So for example, if you have a channel that has a high aspect ratio, you typically have two equilibrium positions rather than an annulus, which you would have for a circular cross-section. If it's a square cross-section, depending on the Reynolds number, you can have 4 or even more, up to 12 or whatever equilibrium positions. But let's take this example here where you have 2. Then what you will often find is that you have a staggered train of particles. And this is, of course, much, much better for microfluidic applications because you can rely on a relatively constant distance between particles in flow direction. That is important. Okay, so the motivation is really, how can we use inertial microfluidics for microfluidic applications where the cell spacing along the flow direction is important? What you see here, that is a PNAS paper from 2010. So you can see it is not that old. It is a relatively new technology. And here you see the same effect, but in computer simulations performed by Christian Scharf and Holger Stark in Berlin, published last year. And they showed that, so it is nowadays possible to simulate this quite easily with lattice-Boltzmann simulations. They showed that the trains that are forming, the staggered trains in this case, they're essentially made up of pairs of particles, okay? So you have maybe the flows to the right. So you have the leading part of the train. There is already a staggered train. And then if you look carefully, you have particle pairs forming first, and then they are catching up from behind and they are extending the train. Now, I'm not exactly sure how they non-dimensionalize time. I think they use a viscous time scale, but later on, I will show you some data where the time is non-dimensionalized in advection times, which basically tells you how many diameters do you have to travel in order to see these effects. And that is extremely important for microfluidic applications, because if you have a channel that has to be, let's say, 10 centimeters long at a Reynolds number of 100, that is typically not feasible because you have huge pressure drops. I talked to experimentalists recently, and they said they have up to 200 bars at the inlet and atmospheric pressure at the outlet. So essentially what happens, at some point you delaminate your chips and you cannot do it. Even if it works in a simulation, in an experiment, you will just not be able to do it, which means everyone is interested in reducing the footprint of these devices, make them shorter in particular, because shorter device means smaller pressure drop at the same pressure gradient. So a bit of background, how do these forces look like that act on the particles? And you have seen that also yesterday in the presentation to some extent. There are here three, I would say three, there are more, but let's start with the 3 most important forces. One of them is the inertial wall lift force. As I told you, in Stokes flow, there is no wall lift force, but in inertial flows, you can come up with a Bernoulli type argument that there is a higher pressure between the particle and the wall forming due to inertial effects. And this pressure is pushing the particle away from the wall. So that is one ingredient to the lateral migration of particles in inertial microfluidics. The second one would be the so-called shear gradient lift force. You always have some kind of a parabolic profile, or it's always curved in microfluidics. You never use a simple shear flow. So you have a curved velocity profile, and typically particles like to go to the region of higher shear in inertial microfluidics. And you can imagine that both forces together, they will find some kind of equilibrium at some point again away from the wall, because they have different scaling behavior with a distance from the wall. So you have 2 competing effects that you have in most cases some kind of equilibrium position that is not on the center line, but somewhere off center. But now the question is, how can you explain particle trains? And for this, you have to talk about the drag forces, because if you have different particles that are approaching axially, then obviously they need to experience different drag forces. How this works in detail is still not fully understood, and I will actually not talk much about forces in my presentation today. Yeah, so I think the important takeaway message here is, due to inertia, you have these lateral forces that lead to lateral migration of particles. and you have secondary flow effects that lead to an axial interaction of particles, resulting in train formation. So what we wanted to do in our study, we wanted to investigate how does a single pair of capsules form and how does it behave? Because if you remember, I told you that particle trains are believed to be made up of particle pairs initially. Particle pairs form and they form the train. So it is worth looking at particle pairs in a bit more detail. And of course, we know that inertial microfluidics is very often used for cells, biological cells, which are soft, in particular at the flow rates we are talking about. So we wanted to look at soft capsules in particular, and I will get back to this diagram in a bit more detail later on. So that is the introduction, the motivation. Just a very, very quick overview of the physical and numerical model. First of all, we have to look at the parameters of our system. What is important? What do we look at? We have a channel, a straight channel in all the simulations because it's just simpler to do and the physics is still not well understood. So instead of going to more complex geometries, a straight channel is sufficiently difficult to understand. In our case, we use a rectangular cross-section with an aspect ratio of 2. Of course, you could use a different one. Then you have, it's all in 3D, we have a plane in the middle between the side walls, and the two particles are initially on the mid-plane, and the motivation is that the inertial migration along or in the cross-section is typically very fast in the way that particles, they form on, you get equilibrium positions here and here typically. So we assume that the particles are already more or less in that configuration. Of course, you could say, well, what happens if you release particles in random positions, but the parameter space becomes absolutely enormous and it's not feasible to do that. So our simplification is we have a 3D simulation, but we put the particles on the midplane. And we also believe that changing the aspect ratio does not make a huge difference because the velocity profile on the midplane is relatively independent of that aspect ratio. It's roughly periodic. So we have a flow speed. Characteristic scale would be the maximum velocity of the flow in the absence of particles. We have two geometric length scales, the half width and the half height of the channel. Of course, we have a particle radius A, which in our case is 40% of the half height, which means our confinement ratio in the channel compared to the smaller dimension of the channel is 40%. Again, this can be changed. 40% is relatively high, but there are some inertial microfluidic applications where you have very high confinement ratios. Also, what we do in order to non-dimensionalize time, and this is very convenient to show how much downstream distance do we need to see what's happening, we use the advection time as typical timescale. We don't use the viscous timescale, which would be, I would say, a bit misleading in this particular application. So it's just particle radius divided by maximum flow velocity. Of course, we can come up with the dimensionless groups. We have the Reynolds number, which we keep also fixed. And 10, it seems relatively small, but for Reynolds number 10, you already have these train effects, at least at higher confinement values. The Laplace number is now an important parameter here because it characterizes how soft the particles are. You can see kappa S, which is the elastic modulus of the particle, of the capsule. Instead of working with capillary number, which we could also do, we chose the Laplace number because the Laplace number is a pure parameter based on material properties. Kappa S is elasticity of the particle, A is size of particle, rho and mu are density and viscosity of the fluid. So the Laplace number is fully characterized by the system we look at, independent of the flow rate. That is quite convenient. And what we have looked at in the study in more detail is the initial distance between the two particles along the flow direction, along the x-axis, and also independently the initial distance of both particles from the center line. And this is important. So if you now count the number of free parameters we have delta x, we have z lead for the leading particle. Leading particle is the one that is initially downstream, that is leading the pair. And the lagging particle is the particle that is more upstream and lagging in the pair. So we have 3 initial parameters, and we have the Laplace number. It's already a lot. So of course we can change Reynolds number, confinement, but the parameter space is getting huge, and we decided against it. In terms of numerical method, nothing new to say here. We use a standard lattice-Boltzmann scheme, in our case BGK, which is perfectly fine for the Reynolds number we look at. We have a finite element model for the capsule. This is how the capsule would look like in its undeformed state. It's initially a sphere. We have an immersed boundary method with a 3-point stencil for the two-way coupling between flow and the capsule behavior. Okay, so what do we see? Now, first of all, we looked at different types of interactions between capsules, and the images you see here are just example images. So not all of the simulations look exactly like that. It's just to show you how the interaction types are different. We have observed 6 different types, and I will start with 4. These 4 you see here have also been found for rigid particles. So there's not much new here, but we know that they also occur for soft particles. So the first one, swap and scatter. Scatter means that there's an interaction that leads in the pair dissolving. So like in particle physics, for example, scattering event means that the distance is not bounded later on. Capture means you form some kind of pair that persists over time. So swap and scatter, swap in this case means that the lateral position of the particles change in a way that initially the lagging particle is faster, it's closer to the center than the leading particle, but then they interact in a funny way so that the lagging particle is pushed closer to the other wall and the leading particle is getting closer to the center and therefore faster, and then the leading particle is moving away. This is what we call swap and scatter. Then we have pass and scatter, and I have a video here. So what's happening, the lagging particle overtakes the leading particle, and it cannot be bothered staying in the pair and just moves on, and that's it. So we have no pair forming, and we have a scatter event. Of course, you could say if there are more particles downstream, then there's another opportunity for a pair to form, of course, but we have looked only at 2 particles here. Then scatter event is very boring. It just means the lagging particle never really catches up and the leading particle is moving away. And capture means that the lagging particle is coming closer and the pair is somehow forming, stabilizing, and it moves as a pair. Now, what is new is for particles that are sufficiently soft, we found that there is swap and capture and pass and capture. And just to tell you what the outcome is, in both cases, we have a pair at the end, but you can see that in one situation, the leading particle is still the leading particle, the initially leading particle is still the leading particle, but there are some few cases, it's actually quite rare, that the lagging particle overtakes, but then doesn't move away. And the pair looks very similar to the other one. The only difference is particles have swapped around. That's a rare event. Also, if you look at the distance traveled for the pairs to form, we have also non-dimensionalized the distance by radius. You can see we are talking about a few hundred particle radii or a few hundred advection times, which are basically equivalent. Not exactly, but roughly equivalent, because particles are typically not moving at the center line where U max is defined. Okay, so I don't want you to understand all of this data here, but just to tell you roughly what we found. First of all, large Laplace number means more rigid particle. So you can consider Laplace 100 as quite rigid. And this is very similar to what other people have found for rigid particle pairs. Basically what you see here, we have different deformability values in the 3 columns. We have different initial axial distances in the 3 rows, and the 2 axes in each diagram give you the initial position, the Z position, the distance from the center line for the leading and lagging particle. Now, I would like to draw your attention to the right half of each of these diagrams, where both Z lead and Z lag are positive or negative. So basically they have the same sign, which means both particles are released at the same side of the channel. And for rigid particles, essentially always this leads to an unstable situation. And we have never observed any train of particles, at least for this confinement value, where both particles form a stable pair and they are both on the same side of the channel. So what we found in all cases, the pairs are either on different sides of the channel or they are actually at the center line. If you now make the Laplace number smaller, which means particles are getting softer, then you can see that there's a bigger, let's call it cross-sectional area that leads to pair formation. A gray background means that there's a stable pair forming here also, but light gray means metastable. I'm not really talking about that here. Metastable means there is some kind of fluctuation still in the axial distance, but it seems to be bound, but it is not really constant. And I will not talk about that. If you want to read about that, you can look at the preprint. So softer particles give you a much larger opportunity to form a pair because the number of initial conditions leading to something like a pair is much, much larger than for more rigid particles. And I think that is very important. Now we can look at different trajectory types and how they change when you change, for example, the lagging position. And here you see something interesting. So typically we find stable axial distances of around 2.5 radii. And we believe that is definitely smaller than what you've seen yesterday in the presentation, where it was 2.5 diameters, I believe. That is also caused by the high confinement ratio we have in this channel. If you go to softer particles, you see something weird happening. And this is that some of them are close to 2.5, but they are not really scattering. The distance remains more or less constant, but there doesn't seem to be a converged distance. And the difference is that the solid lines here are actually pairs where the particles are staggered off center, and the dashed lines are where the particles are more closer to the center line. So we asked ourselves, okay, is maybe the stability of the pair related to the lateral position of the particle? And in fact, this is true. So what we see is that if you look at the lateral position of the particles over time, that if the Laplace number is very small and the particles are very soft, both particles in a pair reach the center line. And there's a critical Laplace number, in this case, I believe around 20, above which the particle is so rigid or rigid enough not to go to the center line, because softer particles have a high tendency to go to the center line due to deformation forces. If we plot the equilibrium position as function of inverse Laplace number, and there's a good reason for that, because the rigid limit is infinite Laplace number. So to show the rigid limit as an actual data point, we have to take the inverse Laplace number. So it's at 1 over Laplace equals 0 would be the rigid limit. And this is taken from a paper by Scharf and Stark. And you can see with a bit of imagination that our data is actually leading to this data point. So we are quite confident that the data makes a lot of sense. Of course, we have also done benchmark tests you can see in the paper. The important observation here is that the leading and lagging particle have equilibrium positions that are virtually on top of each other. You cannot see the difference between the blue and the green dot here. They are basically on top of each other, but the particles are on different sides of the channel. So one of them, and that's why you see the magnitude here, one of them is always at a positive, the other one at a negative Z value. But these values are by magnitude essentially the same, first of all. And second, if you compare with a single particle in isolation under the same flow conditions, even that lateral position is basically the same. So the pair nearly behaves like a single particle in terms of position, location, but the difference is that we of course have the formation of a pair. With a single particle, you cannot have a pair. So we thought, okay, there might be something happening with different orders of contribution of particle effects. And this led us to the idea that maybe we can explain the observations to some extent by looking at different orders of contribution. What I should have said is that the axial arrangement always comes after the lateral equilibration of the particles, also something that Othman mentioned yesterday in his talk. we see that particles first find the lateral position to some degree, and only then the axial position equilibrates. So what we thought then is, okay, we have a zeroth order effect, which is just determined by the flow. So the flow without particle gives us the flow field, the primary flow field, zeroth order. Then we put in one particle, which leads to first order effects. And this is essentially lateral migration of a particle, which you would not see in Stokes' flow, for a rigid particle at least. But in our flow, you can see lateral migration, which happens for a single particle already. So it's a first order effect. And then you have also oscillations between the particles, and you have the axial arrangement between particles, which obviously must be two particle effects, and therefore we call them second order. And it seems that the second order behavior is highly dependent on the first order behavior, which means the system first has to equilibrate on the first order before it can equilibrate in the second order. And what we then did in order to see in a bit more detail how the particles actually equilibrate, we looked again at the lateral positions, and you see, well, particles are oscillating to some extent. They are not moving straight to their equilibrium position. They're actually oscillating a bit, and that must be due to the interaction between both particles, of course. So if you have a two-particle system and you think like a physicist, what do? Of course, you look at, for example, the distance vector between the particles and the center of mass system. So what I find very interesting here is if you look at the distance between the particles in lateral direction and divide it by 2, then you get nearly the same behavior you have for a single particle in terms of lateral position. And the oscillations disappear. So what does it tell us? It tells us the pair oscillates, but it oscillates in a way that the distance between the particles doesn't oscillate. And this means we have a strong coupling between the particles, and that is probably caused by lubrication effects, because if you imagine particles oscillating against each other, fluid would have to be pushed in and out of the gap constantly. And this is, of course, something that the system doesn't want to have. So on a larger time scale, the particles get closer or farther away, depending on what the initial position was. But on a short time scale, where the oscillations are much faster than the migration, these oscillations are damped out in the center of mass system because of lubrication effects. And if you now look at the center of mass movement, then you can actually see that at later stages, we start at the circle and we end up at the equilibrium axial position. At later stages, no matter where you start, the spirals look essentially the same. So the key result is, as long as you get the same final outcome, the system completely forgets about what happened early on, which is somewhat clear because we have a viscous system also. It's not just determined by inertia. It's very complex because we have a viscous and inertia dominated system. But at late times, everything is forgotten what happened at the beginning. And just to close, that is my last observation here, we wondered, how long does it actually take for particles to catch up and form a stable pair, if they form a stable pair, given their initial axial distance? And that is, of course, important for designers of microfluidic devices. So we started with a few radii in axial distance and went up to 11 and measured the time it took until the distance reached its first minimum. And then after that, you have oscillations. And we plotted this time, and we found that this is truly an exponential growth, which means the larger the distances of the particles initially, the longer, exponentially longer it will take for the pair to form, which is extremely important for the design of microfluidic devices. So you can see it can take up to 6,000 advection times for a pair that is 11 radii away in axial distance initially, to form a pair. And if a particle has a radius of, let's say, 5 or 10 micrometers, we are talking about a channel that is essentially too long for a microfluidic experiment. So you will see that only under some circumstances you are able to form your trains that you want to have. You need the right initial concentration of particles to do that. Okay, so to conclude, soft particles show richer behavior in terms of trajectories and dynamics than rigid particles. That is roughly the main finding of the study. we were able to show that we can distinguish between 0th order effects caused by the flow alone, 1st order, single particle, 2nd order caused by 2 particles. And of course, you can have more than 2 particles in a train. And the important bit here is, and this is not really a new finding, it has also been found experimentally some time ago, that typically the lateral migration has to happen before anything else happens. And this tells us that any microfluidic devices that are designed for axial spacing of particles, they are more cumbersome to design than devices where you just want to focus particles at a given equilibrium position. Because you need more space, you have to make sure that the lateral focusing works well initially, and so on and so on. And what we can do next, of course, is we can look at heterogeneous pairs. There has been some work already, but still plenty of work to be done. Heterogeneous in this case means different properties like size, but also diffmobility. And of course, more about particle trains. And eventually we want to look at viscoelastic particles, because at the timescales we're talking about, the viscous properties of cell membranes are definitely important. And with this, I would like to thank the audience for your attention, and I'm very happy to take questions. Thank you.
Thank you very much, Tim. Really brilliant and very interesting talk. Really, thank you very much. Are there any questions from the audience? Let me see if we see in the chat, maybe.
I would have a question. Thank you for the talk. And you mentioned in the experiment that you would have like 200 bars of pressure drop. And the simulation avoids this entirely by driving the flow with a volume force. Theoretically, in the experiment, you could do the same by putting the entire thing in a centrifuge. Would this make sense in the experiment, and is it feasible?
Well, in a centrifuge, you will still build up the pressure, right? Because if you have, let's say, you take a closed tube and you spin it around one end, then you will measure a much higher pressure at the other end due to the radial force, and you will end up with a high pressure anyway. So no matter what you do, you will break your system.
Okay, there is another question from by Alexander Sukov. He tells you that it is a great talk. And when talking about inertial microfluidics, the inertia of the fluid or that of the particles is meant, please.
Yes, so the Reynolds number I mentioned here is the Reynolds number of the channel Reynolds number. But Dino De Carlo showed in, I believe, his first paper about inertial microfluidics that typically it boils down to a particle Reynolds number of at least 1. Well, we all know that there's no magical threshold of Reynolds number 1, and above you have inertia, below you don't have inertia. But they found that indeed, Reynolds number for the particle of about 1 is a very good separation between the region where you don't find inertial effects and where you can see the onset of inertial effects. And in our case, we are at the lower end of Reynolds number. But effectively, you need to look at both. And the relation between them is, of course, confinement ratio of the particle compared to the channel. If you make a particle very small, then you will see that the particle Reynolds number is also small, but the channel Reynolds number can be high.
Thank you very much. Other questions? Alexander, thanks you. Okay, if there are no other questions from the audience,
wait, there is one in the chat. It's about the exponential increase of the pairing time.
I cannot see it. Okay, great, please. Yes, please, Tim. I didn't see it. Okay, thanks.
Right, so I think what is happening is you always have some kind of flow deformation around the particles, right? One particle will create some kind of distortion in the flow field which decays along the channel. So the question is really, up to which point will one particle still see the distortion caused by another particle? And it seems that this will be very small, this effect at larger distances, but it's still sufficient for particles to catch up, or at least the lagging particle to catch up. And we haven't looked at that in detail. That is something we would like to do in the future. We cannot answer your question really, but you can imagine that there will always be some kind of interaction, at least in an idealized system. But in practice, if your channel only has a given length, at some point you will just not see the particles interacting. This is, I believe, how it is.
Okay. Great. Other questions? Okay, I don't see any other questions. So I would like to thank Timm one more time. Thank you very much for this very nice. And
thanks again for the invitation. It was a pleasure.
Yes, it was really a pleasure to have you with us. And please, if you have your free schedule, stay with us for the next talks. Thank you very much, Timm, once again. Then we can split our audience in the two technical sessions that begin now. Technical session number 7 here in Sala Leone, and the technical session number 8 in virtual room Palma. Okay, so we have a few minutes now, just very few minutes, a quick change to welcome our next speaker, Fabio Guglietta from the University of Rome Tor Vergata. Fabio, are you there?
Hi, Giacomo.
Hi, Fabio. Okay, I didn't see you. Okay, great. Can you share your screen?
Okay, trying to.
Giacomo, I'm enabling Fabio to share his screen.
That's great.
Before,
okay.
Yeah. If you want, great. I can share this session. Huh?
That's great. Okay, please take the lead, Andrea. Thank you very much. Thank you very much. Okay.
Okay, Fabio, are you here?
Yeah.
Perfect. And are you okay? Now I make you as an organizer.
Yeah, I think it should be fine now because now I can share the screen.
Are you sure?
I think so. I can try to share, but I think that I can do it.
Okay. So let me introduce you. So this is the technical session number 7 in Biofluidics. The first speaker is Fabio Guglietta, and with the talk on the effect of membrane viscosity on loading and relaxation dynamics for a single red blood cell. I recall that you have 50 minutes plus 5 minutes of question and discussion. So let's start whenever you're ready.
Okay, thank you. Yeah, today I would like to, oh, can you see the screen and the pointer also, right?
Yeah.
Okay, thanks. Today I would like to talk to you concerning 3D numerical simulations to investigate the effect of membrane viscosity on both loading and relaxation dynamics for a single red blood cell. And yeah, I'm Fabio Guglietta, a PhD student from the University of Rome Tor Vergata, the Aachen University, and the Cyprus Institute. So let's start by looking inside a small drop of blood. What can we see if we use, for example, a microscope? Well, we can see, of course, red blood cells, white blood cells, platelets, and all of them are immersed in a Newtonian fluid called plasma. So what's important to look at is the concentration of these components, because the 55% about is made of plasma, that is, I said, Newtonian fluid, while the 41, 42, it depends on the healthy state, on the age. However, almost the 40% is made of red blood cells and is also called hematocrit, while the remaining part is made of platelets, white blood cells, and other stuff. So this concentration explains why it's very important to study red blood cells, and in particular the viscoelastic and mechanical properties of red blood cells, because they are the main constituent of the blood. So this is a typical experiment that is done to investigate the mechanical properties of red blood cells. Here you can see a red blood cell, a single red blood cell that is stretched by using optical tweezers in order to investigate, for example, the loading relaxation times. And what we want to do is to perform 3D numerical simulations to reproduce this kind of experiments, and also other new setups. So to perform 3D numerical simulations, as also before Professor Krüger said, we need first to model the viscoelastic membrane, and to do so we can use a finite element method. Then we need to simulate the fluid both inside and outside the membrane, and for this we will use a numerical solver. And finally, we need to couple the membrane and the fluid. I will show you now a couple of slides to explain this, but I don't want to spend much time on this, otherwise there will be no time for the results that are the most important part of the talk, I hope. So this is a sketch of the 3D triangular mesh used to simulate the viscoelastic membrane of a red blood cell. And this is a zoom on the surface where you can see the two neighboring triangles. composing the mesh. So to account for the viscous effect, we can define a viscous tensor here, which can be split into parts, one accounting for the shear membrane viscosity and the other one for the dilation membrane viscosity. Even if for red blood cells, it seems that these two values of μs and μd are equal, and their value is μm, so the viscosity of the membrane. So this tensor simplifies in this expression here. And while for the elasticity of the membrane, we accounted for the strain energy by using the Scalac model and then bending energy with Elfrich formulation. So this term here is the resistance against the strain, while this other term here is the resistance against the bending. So the bending between two neighboring triangles. Once we have computed both the free energy, the elastic free energy, and the viscous stress tensor, we can compute the viscous force and the elastic force on each node. And then we put them together, and we have the total force acting on a single node. Then we can solve the fluid by using the Lattice-Boltzmann method. In particular, we use the BGK collision operator and the Guo scheme for forcing. And we differentiate between outer nodes and inner nodes because the viscosity of the inner fluid and the outer fluid are different, and the viscosity ratio is 5. So the fluid inside is 5 times, the viscosity of the fluid inside is 5 times higher than the fluid outside. Here is a 2D sketch of the membrane that can be represented by a set of Lagrangian nodes that are the nodes where we computed the force before. And then this force can be communicated to the fluid by using the Immersed boundary method. And then the force enters in the Lattice-Boltzmann equation. Finally, we compute the fluid velocity with the Lattice-Boltzmann equation. And we communicate this fluid velocity again with the Immersed boundary method from the Eulerian nodes to the Lagrangian nodes. So the membrane can deform and evolve during the flow. Okay, let's move to the results. So the first question is, what is the effect of membrane viscosity on the loading and relaxation dynamics? To answer this question, we build up a simulation that is called a stretching simulation, in which we are simulating the stretching in optical tweezer. So we can see here the two silica beads used to stretch the red blood cell, and by applying two forces with opposite direction. And we measure the axial and transversal diameters. And this information is used to compute the Taylor index, which measures the deformation of the cell. So this is a short movie explaining the simulation. As you can see here, we are not actually simulating the two silica beads. We just select a few nodes in these areas. That is the area where the silica bead is attached. And we stretch directly the red blood cell here. So we apply the force. The red blood cell deforms. We measure the axial and transversal diameters. Then the force stops, and the red blood cell relaxes to the shape at rest. So this is the whole process of loading here and then relaxation. And here in this plot, I am reporting the deformation as a function of time for two different values of membrane viscosity. In particular, the dark brown here is a higher value of membrane viscosity. Qualitatively, we can see that the effect of membrane viscosity is to make the dynamics slower, both loading and relaxation. But if you want to quantify both the loading and relaxation times, we have to fit this deformation with these two functions defined here, one for the loading and the other one for the relaxation, which depends on two parameters. The first one is the characteristic time, that is TL or TR, depending on the loading and relaxation. And the other one is this delta exponent, which used to account for multiple relaxation times or multiple loading times that emerge during the loading and the relaxation. So this is the result for both characteristic times, loading and relaxation. And what we can see is that increasing the value of membrane viscosity, the result is an increase of both the two characteristic times, while increasing the external force results in a decrease of the characteristic times, both for loading and relaxation. But now we want to see if this is, how can I say, a universal property, or it is experimental dependent, simulation dependent. So we perform another kind of simulation, that is the shear simulation, where now the red blood cell is deformed by an external shear flow whose intensity is quantified in terms of the shear rate dot gamma. And again, the red blood cell deforms, and we measure the axial and transversal diameters to compute the Taylor index. So this is a movie again. Now you can see that while the red blood cell deforms with a shape, CD shape, it still rotates. This is the puncturing motion of the membrane. And then when the flow stops, the RBC does not rotate anymore, and it just relaxes to the shape at rest. So this puncturing motion is important, and we will come back on this later. However, again, this is the full process of loading and relaxation. And here we are reporting again the deformation. Now there are two main differences here. If compared this with the stretching simulation. Oh, sorry, this is shear simulation, not stretching simulation, sorry. And the first difference is that now the deformation, the average deformation depends on the value of membrane viscosity. And in particular, it seems that increasing the value of membrane viscosity results in a decrease of the average deformation. But now we also have these oscillations. So we, to fit this data, we cannot use anymore the function that we used before, but we need to add this cosine function here. So with another characteristic time, this TL cos here, which accounts for the oscillation, and it measures the period of these oscillations that are damped in time. And so those are the results. And we can see that the period of the oscillation does not depend too much on the value of membrane viscosity. There is a collapse of the values for different value of membrane viscosities, while TL and TR, so the loading and relaxation times, almost behave as for the stretching simulation. So increasing the value of membrane viscosity results in an increase of the 2 times. So to answer the first question that was, what is the effect of membrane viscosity on loading and relaxation time? The answer is that increasing the membrane viscosity results in an increase of the 2 times. But now we also understood that these 2 times are not universal, so they depend on the kind of mechanical load, because those are the results for the stretching that are different from the results for the shear simulation, even if the value of the times fall in the same ballpark. But now we want to go further in the investigation, and we want to ask if there is a symmetry between loading and the relaxation dynamics. To answer this question, we first define tilde t, that is the ratio between the loading time and the relaxation time, and we want to see if this ratio is equal to 1 or not. So we start again with the stretching and shear simulation, and we found that for the stretching simulation, tilde t collapses on a mass recur, so there is no dependency on the value of membrane viscosity, while for the shear simulation, it still it depends on the value of membrane viscosity. But however, in both cases, there is no symmetry. So we want to understand why there is this difference. And if we look at these two simulations that are the stretching simulation and the shear simulation, we can see that in one case, so in the stretching simulation, the membrane does not rotate while deforming, while in the shear simulation, the membrane rotates. So this is the first difference. And then I don't know why it stops. Another difference is that in the stretching simulation, the membrane is directly forced by putting a force directly on the nodes of the mesh, while in the shear simulation, the membrane is not directly forced, but it is forced by viscous friction with the fluid. So we want to understand what is the problem here. So if it is the rotation of the membrane or the fact that the membrane is deformed by viscous friction. So why there is this lack of collapse? If we look at the velocity gradient, we can split it into parts, one accounting for the rotation and the other one for the elongation, the membrane. And what we want to do now is to perform a simulation which removes this rotation and has only the elongation apart. To do so, we perform this 4-roll mill simulation where there are 4 rotating cylinders here deforming the red blood cell by the flow. So now the membrane does not rotate anymore. So this is like the stretching simulation, but now the force is not directly put on the membrane. So it is like the shear simulation. So this is a mixture of the two simulations. Okay, this is a sketch of the simulation. You can see the cylinder rotating. Those are the flow line. the membrane deforms, then the cylinders stop rotating, and the membrane relaxes to the shape at rest. Well, here again, we had a plot for the deformation as a function of time, and we can see that now there are no more oscillations because the oscillation that we saw before for the shear simulation are typical for when the membrane rotates. And this plot is similar to the one for the stretching simulation. So again, we use the loading function used in the first case for the stretching. And those are the results for loading and relaxation time, which behave like in the two previous simulations. But now tilde t again show the same collapse as for the stretching simulation. So it means that now there is no dependency on the value of membrane viscosity as for the stretching.
2 minutes, Fabio.
Okay, thank you. And here is a comparison of all the three simulations. And what we can see if we focus on the stretching and forward mist simulation is that we can think to factorize both loading and relaxation function that are function of the stress on the particle and the value of membrane viscosity as two contributions, one coming from the stress of the particle and the other one from the value of membrane viscosity, both for stretching and forward mist. Why this? Because when we compute tilde t, that is the ratio, the two contributions coming from the value of membrane viscosity disappear. And it remains just a function of the external forcing or the stress of the particle. And I just want to spend a few words on the importance of membrane viscosity also on the steady state, because while in the stretching and forward mist simulation, the steady state of the deformation does not depend on the value of membrane viscosity, in the shear simulation, it still depends. Indeed, here I'm reporting the deformation for the stretching simulation, and all the values collapse on the same master curve. And also in the forward mist, there is the same scenario. While in the shear simulation, we can see that increasing the value of membrane viscosity results in a decrease of the deformation. So to conclude, the effect of membrane viscosity is to increase the characteristic times. And we can see a symmetry between loading and relaxation when the external force goes to 0. So it means that we are looking at the intrinsic properties of the membrane, while otherwise there is an asymmetry of the two kind of dynamics. And this depends on the kind of mechanical load. In particular, we showed the role of the rotation in this. And moreover, the membrane viscosity can also affect the steady state, not only the transient dynamics. And that's all. Thank you for your attention. And if there are questions, I'm happy to answer them.
Okay, thank you so much, Fabio. We have time for questions.
Okay.
Okay, there is a, let me check here. Otmane Awane, I think. Fabio, before proceeding, I upgraded you as an organizer. I made a mistake. Now yeah, okay. No, could you please, yeah, because I lost all my privilege and now all the conference is on your shoulders, basically. So
okay.
You can, okay, now I'm the organizer. Okay. Okay, I think you can speak, Awane.
Yeah, okay. Thanks. Okay, yeah. So very nice talk. Thanks a lot, Fabio. Okay. I have a quick question. So my feeling is that the stretching experiments apply a force which is normal to the membrane. So you are stretching the membrane. And the four-roll experiments are also applying a kind of similar force, which is basically also leading to a stretch of the membrane. So I am not surprised that both results looks more or less similar. While, for example, for the shearing experiments, what you are involving is basically in plane forces. So basically you are applying forces which are tangential to the membrane. That's basically lead to a different behavior. And if we compare then the shear experiments with the four-roll and the stretching experiments, then we see, for example, that the membrane viscosity is playing an important role when you are applying in-plane forces. But when you are applying out-of-plane forces, so normal forces to the membrane, then the role is less important. I would put it this way.
Actually, I think that even in the forward mist simulation, there are not only normal forces, because there is a distribution of forces on all the membrane. And the stretching simulation is exactly how you said. So I am just applying a force on a small portion of the membrane, and it is almost normal to the membrane. But here, actually, I'm applying a force on all these points of the membrane. So there is a distribution of the force on all the membrane with a different density of force on the membrane.
But the results is leading to stretching.
Yeah, the results is the same.
Yeah.
And in particular, I think that the reason is that the energy that I'm injecting with an external force, in this case, so in the forward move and the stretching simulation goes in the deformation, only in the deformation, while in the shear simulation, it goes in part in the rotation, and it is not, how can I say, equally distributed, so it can affect also the characteristic times. I think this could be the reason.
Okay.
Okay.
So maybe later for the future, if you just want to do one thing.
Sorry, we should move on.
Yeah, okay. We can continue later.
Okay, thank you.
Thanks a lot for the talk.
Oh, thank you for your question.
Okay, thanks again, Fabio. Now let's move on with the second speaker of the day, of the session, which is Zeli. Zeli, could you hear me?
Yes, I can hear you.
Okay, perfect. Now you are co-organizer, and I can see your screen. As always, you have 15 minutes plus 5. Okay. So
okay.
Start whenever you want.
Perfect. Thank you for the introduction. I just want to remove all this. Sorry. Just some technical problem because the camera just catch this. Okay. All this information in my screen.
First of all, I can introduce you. So next speaker is Lee, and the title of the talk is Coupling of LBM and FEM with the implicit IBM for numerical simulation of blood flows through the aortic valve.
Okay, thank you very much. Good morning, everyone. My name is Zeli, and I come from École Centrale de Nantes in France. So today I'm happy to talk about our recent work, which is about the coupling of lattice Boltzmann method and the finite element method with an implicit immersed boundary method for the numerical simulation of blood flows through the aortic valve. So today, after a very brief introduction of the context of the present work, I'm going to show the numerical formulation of the two numerical methods that have been used in our work, which is the lattice Boltzmann method and finite element method for the fluid and the solid, respectively. And then I will just present the adopted implicit immersed boundary method to couple these two numerical methods. And then I will just show the coupling algorithms followed by some numerical validations and applications. And finally, I will finish my talk with some conclusion and perspectives in the future. Okay, up to now, the cardiovascular diseases are still the leading causes of death based on the WHO's estimation. In the year of 2019, almost 18 million people died from the cardiovascular disease. Well, various types of CVDs, in fact. Well, among these CVDs, valvular heart diseases are some, is an important family of this CVD, which is usually related to the failure or dysfunction of, let's say, from 1 to 4 heart waves. For example, stenosis or regurgitation. Well, in this case, it is usually necessary to carry out a surgical repair or repairment of the heart waves. Recently, some transcatheter techniques have been developed and widely used all over the world, such as the transcatheter aortic valve replacement, or in short, TVAR. Well, although these techniques have been allowed to use since almost, more than 10 years. In fact, for the surgeon, it is not always very clear to find the optimal operation strategy. In addition, the long-term influences to the patients are not still very clear. So the objective of the present work is to propose a numerical coupling framework in order to build up a virtual surgery platform in which we start from the not experimental, but the measurement in the hospital using the MRI, for example, in order to get the geometry of the anatomic condition of each patient. And then we send this information to the numerical simulation framework. And then we can carry out a series of different numerical simulations. And then this will provide us some suggestions to the surgeons to finally choose the optimal strategy in the realistic operation to the patient. Okay, so in this work, in order to simulate the blood flow, we choose to use the lattice-Boltzmann method, which is very efficient, which can be efficiently parallelized. And in this work, we choose to use, let me just use this, LBE, which is based on the force model of Gould, proposed in 2002. And in this work, we have used two types of lattices. In 2D is 2D D2Q9, and 3D is D3Q19, which are sufficient to simulate isothermal weakly compressible blood flows. And here, this is the equilibrium distribution function, and this is the body force related term. And since we used the force model of Gould, we have to sort of correct the velocity using this body force related term. Okay, and since the single relaxation time LBE, LBM sometimes suffers from the numerical instabilities, so we have chosen to apply the regularization procedure in order to stabilize the simulation, especially when the Reynolds number is relatively high and in the presence of moving solid boundaries. And here we, as you can see, that we have used the regularization procedure based on the Hermite polynomial expansion. Q is the expansion coefficient, H is the Hermite polynomial. And in the present work, we choose to truncate this reconstruction of the non-equilibrium part of the distribution function up to 2, which is sufficient to for simulating isothermal weakly compressible flows. And finally, this is the regularized LBE, and as you can see that with this regularized non-equilibrium part of the distribution function, all the right-hand side terms are, relied on the subspace spanned by the Hermite polynomials. And on the left hand, we have this regularized post-collision distribution function. Well, at this point, I'd like just to share an experience, one of our experiences, which is that when we initially when we try to apply this regularization in the numerical simulation involving immersed with solid moving boundaries, we start to reconstruct the non-equilibrium part from the second order. Well, because theoretically the first order, the zeroth order are supposed to be 0. However, we observed something weird, is the force was not correctly simulated. And after a very rapid analysis, we found that if we use the force scheme of Gould, we have to start the reconstruction from the first order, because the first order still contains something. It's not strictly equal to 0 because of the force model. And we have published our analysis in 2019 in the Computers and Fleas. For the solid structure, we choose to use the finite element method and the total Lagrangian formulation in order to take into account the geometrical nonlinearity, which is due to the large deformation and the displacement of the valve. And after numerical discretization, we can obtain this semi-discrete system of equations, which is the one shown in the middle of this slide. And in order, here Qext is the external nodal force, and the Qint is the internal nodal force. MS is the mass matrix. And in order to integrate the system in time, we choose to use a Newmark time integrator. Specifically, it is the explicit version of the numerical scheme, which is conditionally stable. Well, regarding the material models, we choose to use the neo-Hookean isotropic hyperelastic model, just as done in the paper of Siguanza in 2018. And by deriving this string energy density function with respect to the grain string tensor, we can obtain the second Piola-Kirchhoff stress tensor. And in order to validate our implementation in our in-house code, we just apply the same uniaxial tensor test as done in the paper of Siguanza, and we obtained almost exactly the same result. So this validates this implementation of the material models. Well, since the LBM and FEM are two numerical methods of two different fashions, Euler-Ring and Lagrangian, so the coupling between these two methods is not very straightforward. In this case, we choose to use this implicit version of immersed boundary method initially proposed by Wu and Xu in 2009. Well, the idea is to find out simultaneously the immersed boundary related force on all the Lagrangian points simultaneously, so that finally the interpolated fluid velocity is exactly the same to the velocity of the solid boundary. And as you can see that here at the spreading stage, the J's LB node will receive a force from the K's LB point. It's a force from K to J. And if we, by means of the Newton's third law, if we use this formulation to compute the force applied from the fluid subdomain to the K's immersed boundary, we can assure exactly the conservation of linear momentum. And as you can see that this term is simply the interpolated fluid density at the K's point. Okay. Well, regarding this coupling system of equations, well, let us first look at the fluid coupling equations. Here, I just write the definition of the macroscopic fluid velocity for all the LB nodes. Here, you can imagine that the size of this matrix is very large because it contains all the lattice nodes. Well, in practice, in fact, we never need to build up this matrix. I just want to show this, the coupling equation in this way in order to show that our coupling algorithm is a strong coupling system. Well, very briefly speaking, finally, we can write this fluid coupling equations in this way, well, in which only VF and lambda are unknown. Similarly, we can write the solid equations in the same way. And since we have only, we have just two equations, but three unknowns, we need another equation to close the system, which is the velocity continuity condition across the interface. Or in this equation, LF and LS are just the two interpolation operators. So finally, we can build up a strong coupling system of equations like this, as shown in this slide. And it's a system of very large dimension. Well, if we solve this system of equations in the same solver, well, then this is the so-called monolithic coupling procedure. However, we will not do this because first of all, the system is very large. Well, second is that we cannot make use of this modularity of different solvers. So in order to solve this strong coupling systems in the strong way, we just need to do some manipulations. And finally, we just need to first solve the interface force, which is of very small dimension. Well, I mean, comparing to the initial system. And this is the schematic view of this coupling system, coupling algorithm. And just before the showing the numerical validation, I just mentioned that it is not always easy and sometimes impossible to carry out the simulation using the identical time steps. So in this work, we proposed a simple strategy based on the linear interpolation in time in order to replace the costly operations or computations by some very fast linear interpolation. Well, due to the time limitation, I will just pass this part and I will show you the numerical validation, some of the numerical validations we have done recently. The first test case is about a mechanical valve. In here, you will see that you have a 2D channel, and the black part are the fixed rigid solid wall, and the right bar is also a rigid wall, but it can rotate freely around the point O, the XO. And we impose in-light velocity at the in-light as shown in this figure. It's a periodic and a positive in-light velocity condition. And we do some mesh conversions, and by comparing with the references, we observe that, I mean, among all the numerical results, our numerical results agree well with the references. And this is the comparison between the experimental PIV measurements carried out in the reference with our numerical result. And as you can see that at this different 5 instances, the velocity fields are agree well between our result and the experimental measurement using the PIV technique. The second validation test case is a 3D flapping flag test case, which is initially conducted by Huang in 2010. Well, on the right-hand side, as you can see that the displacement and the drag are in good agreement with the reference, with the references we have compared with several different numerical methods. Well, here you can see the vertical structures in this test case. Here on the left-hand side is the case of Reynolds number 200, and the right-hand side is the Reynolds number 500. As you can see that there is, I mean, the vertical structures are relatively, there is still some differences because the Reynolds number are not the same. So finally, I will show you the last case about the aortic valve, blood flow through the aortic valve. Well, here the configuration is the same. In fact, we propose this test case in order to reproduce what have been done in the paper of Siguanza. And at the in-light, we impose a postal and a periodic volume flow rate. And when the volume flow rate attains its maximum value, at this moment, the Reynolds number is about 3,000, which is the order of magnitude of the realistic biomechanical situations. And in this slide, we compare the opening area of the valve at different instants. First row is the experimental measurement of the reference. And second row is the numerical result. Numerical result, and the third row is our numerical result. As you can see that globally they agree quite well, except that in our numerical simulation, the valve is closed a little bit earlier than their result. And this slide shows the vertical structures at 4 different instances. And as you can see that they are quite similar. And finally, this film just to show this evaluation of the blood flow and the valve during 1 second, during one period. Well, okay, so finally, I will conclude my presentation. In this work, we just proposed a partitioned framework to coupling LBM and FEM using the implicit IBM. And this coupling algorithm can be categorized as a strong coupling even without subiterations during each physical time step. And using this interpolation in time, the coupling framework is more flexible to simulate realistic biomechanical applications. And this coupling algorithm has been validated by several test cases, including the blood flow through the aortic valve. Well, in the future work, we plan to implement or to couple the self-finite element method for the valve in order to further improve the coupling efficiency due to the numerical stability criterion in the finite element method. And finally, we hope that this, in fact, we have a project ongoing, and we will work with the doctors or surgeons in the hospital and someone to doing the experimental measurement. And we hope that this framework, numerical framework, will be used in our future surgery platform in order to hopefully save lives or reduce the pain of the patient in the future, hopefully. Okay, so thank you very much for your attention. I'm open to any questions.
Okay, thank you so much. We have time for one quick question. Okay. Write it on the chat or raise your hand. Let's wait. Okay, there are no questions. So thank you again, Lee. And I think that now there is the coffee break. So yes, we will reconnect in 20 minutes. Okay.
Thank you.
Okay. Thanks again. The following speaker is Caterina Scardola, and the title of her talk is Investigation of Blood-like Fluid Flow in Stenotic Arteries using the Laplace-Boltzmann method. Right? Okay. So please, the floor is yours, and feel free to start.
Okay, thank you for the introduction. So, as you said, yeah, also good morning, everyone. And today I would like to talk about investigation of blood flow in stenotic arteries, which is a topic I have been working on together with my colleagues from Czech Technical University in Prague. And I would like to start this presentation with motivation. So I would like to briefly explain what stenosis is and why it might be useful to model the blood flow in such area. So stenosis is abnormal narrowing of the blood vessel, and it may have several causes. So it might be caused by abnormal muscle growth or by buildup of fat, cholesterol, or other substances on the artery wall. And while the first cause usually occurs in childhood and it is not fully understood, the second may lead to stenosis like due to aging or high cholesterol levels or other reasons anytime in the life. So after some time, the buildup of such substance usually hardens and it may limit the blood flow. So it can be also, there is a risk that piece of the plaque may break off and flow to smaller arteries, where it might block the blood flow completely or even lead to a stroke. So it can be treated surgically by removing the plaque and in some cases also by placement of a stent, which is a meshed tube that should keep the artery open. There is, however, a risk of a reoccurrence of stenosis in the same region, so-called restenosis. So the patient should be followed even after the surgical treatment. Besides from these problems, there is also the concern that the long-term effects of turbulent flow that may occur behind the stenosis may lead to some medical issues later on, and also the effect of the turbulent flow on red blood cells is being studied. So apart from this, like more medical reasons why we should be interested in blood flow in such region, there is also the topic my colleagues have studied and published last year, and that is that the turbulence that occur in such region may corrupt the measurement of blood flow in magnetic resonance. So this means that if you want to measure the blood flow to see how severe the stenosis is, we actually don't get as accurate results as we would like. So these are all motivations why we should be interested, or why we are interested in modeling blood flow in stenotic arteries. Now, what was our objective in this much smaller project was to find out whether the non-Newtonian properties of blood are significant and need to be included when modeling such blood flow, or if they can be neglected. And as was already mentioned in the previous presentations, while the plasma is essentially a Newtonian fluid, blood as a whole is not, because of the other components such as the red blood cells. The studies, however, show that while in small arteries the non-Newtonian effects are significant, in larger arteries they are not, and they can in fact be neglected. So our question was whether in large stenosed artery this assumption still holds, or if we need to incorporate the non-Newtonian effects. And we studied this problem in a case of two-dimensional geometry of such vessel. So let's now see the mathematical model. So the dynamics of incompressible fluid can be described by these two balance equations, where rho is density, u is velocity, p is pressure, and t is viscous stress tensor, g is acceleration. And we added some additional assumptions to modify these equations. So first, we only considered one type of the non-Newtonian fluid, and that is generalized Newtonian fluid. This allowed us to use following formula for the viscous stress tensor, where n is the viscosity, and we also know that this viscosity should be a function of shear rate. So apart from this assumption, we also assume that the spatial variation of viscosity are so small that they can be neglected. And if we combine these two assumptions, the balance equation 2 is transformed into this equation, where the viscous stress tensor was replaced by this term. There are several models for generalized Newtonian fluid, and in our work we used Karo-Yasuda model, which prescribes following formula for the viscosity dependent on the shear rate. So on the right side, you can see two limit viscosities, n is infinity and n 0, and then there are three other parameters, lambda, a, and n, and here is the shear rate. So the limit viscosities represent the limit viscosities for shear rate going to 0 and infinity, as you can see in the figure below, where, as I said, the for shear rate going to 0, the black line tends to the limit case n 0, while as the shear rate increases, the viscosity decreases to the at the limit case near infinity. And to simulate blood-like fluid, we used such setting of the parameters which was proposed in this paper from 2007. And that's about our model. For the numerical simulations, we used Lattice-Boltzmann method, which uses mesoscopic description of the fluid for solution of incompressible Newtonian fluid flow, in our case, given by equation 3. The unknowns are the discrete density functions f with index k, and the evolution of these density functions is given by discrete Boltzmann equation, where on the right side we have discrete collision operator and discrete source term. We performed our simulation in 2D, so we used a scheme with 9 discrete density functions and also 9 discrete macroscopic velocities, as you can see in the picture below. And we used cascaded Lattice-Boltzmann discrete collision operator and following discrete source term. Then to reconstruct the macroscopic velocities, we used following formulas. So as I said, in this form, the Lattice-Boltzmann method can be used to for Newtonian fluids. So we needed to do some changes to simulate the non-Newtonian fluid, and we used a method proposed by Van and Ho in 2011, and it in general adds some additional term g, which helps to deal with the viscosity. So if we once again recall what equation 3 looked like, there is the problematic term with the viscosity that for non-Newtonian fluid is not constant. So what is done is that we introduce this additional term g, and we modify this term. And when we look at what g looks like, we see that the non-constant Carrier-Pseudo viscosity is hidden inside this term, and in the modified term there is the constant viscosity. Then we can add this additional source term to the discretized source term that we already have, and that is how we incorporate the non-Newtonian effects. Now let's see the setup of our numerical studies. So we used, as I said, 2-dimensional geometry of stenotic artery. We used MRI-based geometry adapted from this paper. It was already used by my colleagues in previous work. And if we denote the width of the vessel in the stenotic region by W and the width that the healthy vessel would have W0, then we can classify the 3 cases we used in the following way. So first we used the original geometry where the width was approximately 1/2 of the width of the healthy vessel, and then we created 2 more cases with more severe stenosis, so it was 1/3 and 1/4 of the width of the healthy vessel. As you can also see, the original domain from 0 to 100 was prolonged on both ends to limit the effects of the boundary conditions. On the inflow, we prescribed a fully developed velocity profile between 2 parallel plates, and on the other end, we prescribed free outflow condition. So there are 3 quantities we compared to illustrate the difference between the non-Newtonian regime and the 2 Newtonian regimes, and that is mean velocity magnitude, velocity magnitude, negative horizontal flux, and difference between viscosities. And all these quantities were time averaged using this formula, and also the negative horizontal flux was also averaged in space across this cross-section of the vessel. So that is, I think, everything you need to know before we see the results. So in this first slide, there is the mean velocity magnitude, which, as I said, was averaged in time using the formula. And you can see 3 columns, where in the first column there are results for the 3 levels of stenosis using the Newtonian model with the limit viscosity n0. Then there are results for Newtonian model with the other limit viscosity n infinity. And in the third column, there is the non-Newtonian model with the Krüger viscosity. And what we can see is that for the least severe stenosis, all models provide relatively similar results, while for the more severe stenosis, we can see some differences, but we can still say that the non-Newtonian model and the Newtonian model with the limit viscosity n infinity provide pretty similar results. The other quantity we were interested in is the backflow, or the negative horizontal flux behind the stenosis. So in this visualization, you can only see the area of interest, so, from the stenosis on. And here we can see that even for the least severe stenosis, the model with limit viscosity n0 provided underestimated values for the backflow, while again, the 2 other models provide quite similar results. This can be again seen in this slide, where the backflow is averaged also in the space. So we can see that the black line, which corresponds to the non-Newtonian model, and the red line, which is the Newtonian regime with limit viscosity n infinity, are pretty much the same. And this can be this can be explained when we look at the viscosities. So here on this slide, there is the difference between the non-Newtonian viscosity and the limit viscosity n infinity, divided by the difference of the 2 limit cases. And what we can see is that with increasing severity of the stenosis, the viscosity behind stenosis decreases, and it gets much closer to the limit case n infinity. So we see that if we want to be able to model the behavior behind stenosis, this limit case is much closer than the other one. So if I should conclude the presentation, our question was whether Newtonian model is feasible approximation if you want to simulate a blood flow behind stenosis on a large artery. For this case, we used 3 aorta geometries only in 2D, and we created them with increasing severity of the stenosis. For the non-Newtonian fluid, we use Krüger model, and results of this model we compared to the 2 limit regimes this model has. So it's regime with viscosity n0 and n infinity. And what we have seen is that the stenosis, or the severity of stenosis, have impact on the fluid viscosity, that the viscosity behind stenosis decreases with increasing severity of the stenosis. So our conclusion was that for this case, the Newtonian approach is applicable, but we need to choose the right limit viscosity. And after the acknowledgements, that's everything for me, and thank you for your attention.
Okay, thank you so much for this very nice presentation. We have time for questions. If someone in the audience has some question, please raise your hand or write it on the chat. No, I have a question. Sorry, the simulation that you showed us are 2-dimensional, right?
Yes.
Okay, but do you think that there is some 3-dimensional effect that could, I mean, have an impact on the results or on the conclusion that you've drawn?
Yeah. Well, yeah. I think possibly.
Are you planning to make?
Yeah. We are definitely planning to move to the 3D case. Also, I think if we used more realistic geometry, that wouldn't be so ideal. So, for example, it wouldn't be symmetrical, like rotationally, I think 3D would be, I think, necessary to see to see what's really going on. But in this very simplified geometry, I think it was okay to stay into 2D.
Enough. Okay, perfect. Okay, thanks for the answer. Okay, so thanks again for the talk, and I think we should move on to the following speaker. That is, let me take the program because I don't remember. Okay, the next speaker is Rodrigo Coelho. I don't go wrong. You should be here.
Yes, I'm here.
Ah, okay, you're here. Perfect. Let me enable you as a co-organizer. Hi, Rodrigo.
Let me then share my screen.
Share your screen first, and then I present you. Okay, perfect. So the last speaker of this second branch is Rodrigo Coelho with the talk with the title "Effects of Elastic Anisotropy and Active Anchoring in Active Kinematics." So.
Yeah, thank you for the introduction. And sorry, I had changed slightly the title, but the subject is the same. As already mentioned, my name is Rodrigo Coelho from CFTC, University of Lisbon, and I'm going to present our recent work on the dispersion of activity in active kinematics. We can understand this as a model for the dispersion of nutrients in a colony of bacteria, for example. Here. Then, what are active kinematics? This name comes from the passive kinematics, which are the passive liquid crystals used in display technologies. And the difference for active kinematics is that they are composed by particles able to extract energy from the environment and convert it into directed motion. So both the passive and the active kinematics are composed by elongated particles, which are densely packed. So it is important because they tend to align according to their neighbors. So, and examples include colonies of elongated bacteria, as you can see here, and even macroscopic systems as shoes of fish. Here on the left, you see a video which shows a mixture of microtubule kinesin. These are components of the cells. And if there is no nutrients, they are static as in the passive liquid crystals. But when nutrients and oxygen are present, they behave in this chaotic way. They develop what is known as mesoscopic turbulence. They share many similarities with fluid turbulence, but it occurs for low Reynolds numbers. And the question we want to answer here is if there is heterogeneity in the activity field, how would it disperse? Or can think more practically, if you have a passive domain and you drop a droplet of nutrients, how would it spread? We can expect, for instance, that the higher the concentration of nutrients, the higher it would spread, because there is also advection. So the model we use here, it couples an usual model for the literature for active kinematics. This was first proposed by Leone's group, and we ourselves have used it in previous publications. And we couple this model with an advection diffusion equation for the activity field. So this model is a continuum model. We are not worried with the individual particles. We are interested in averages. So for instance, here we have some particles pointing different directions, but in average, they point in the direction of this arrow that you call the director field. This director field is represented by this letter M, and the global, and we model using this tensor order parameter, which has a scalar order parameter that is 0 if the particles point randomly, and if it's different from 0 if they point in a preferential direction. This model accounts from the alignment of the particles with the flow. They change in a certain way depending on the vorticity and on the shear rate. And this change in the direction depends on their shapes. So if they are more elongated, they tend to align more with the flow. The particles tend to align according to the neighbors, and if there are distortions, this has a cost to the free energy. And to make the system move, so on the top you only see ingredients for the passive liquid crystals, and here that's how we make on the model the system to move. So we add this active stress, which is proportional to this activity parameter zeta. And in the previous models in the literature, this parameter, this quantity was constant in time and homogeneous in space. The difference here is that we couple this quantity, zeta, with an advection diffusion equation that gives the time evolution of this activity field. So to show here some equations, the most important ones. The first one is the Beres-Edwards equation. This gives the time evolution of the order parameter Q, and it needs the velocity field here in the second term, and also here in the third term, draw the vorticity and the shear rate. The last term accounts from the minimization of the Landau-de Gennes free energy. This first equation is solved using finite differences, which use the same discretization as the Letts-Bolt method using to recover the Navier-Stokes equation. So the Navier-Stokes equation is the usual one, plus some additional terms that are circled here in colors. These extra terms are implemented by means of a forcing term. So the first one accounts from the friction, because we consider our active kinematic as being on a substrate. This term in red is the term coming from the liquid crystal theory. This is present for passive liquid crystals as well. And the third term comes from the active stress that I mentioned. The last equation is the advection diffusion equation, as usual, but for this parameter zeta. So we have a coupling between two equations with the Navier-Stokes equation. The first one gives the order parameter Q that is used here in the last term and also in this stress tensor, and the Navier-Stokes equation provides the velocity field. While for the advection diffusion, the Navier-Stokes provides the velocity, and the advection diffusion provides the activity, which will be used here in the last term. So we have a very rich system of equations that lead to complex flows and develop many instabilities here, as I will show. The setup we use to investigate the dispersion of activity is basically one dimension, where we start from a Gaussian profile of activity here in the center. The velocity is initially 0, and the directors point in random directions. So after some time, we see that there is advection. We see some defects leaving the active region and going to the passive one. These are these positive defects that are self-propelled, and they carry some activity behind them. After some time, they get stuck here in the passive region because the activity disperses. But there are also defects coming from this region, the almost passive, and going to the active one. So this is responsible from one effect that I'll show in the next slide, that you observe subdiffusion. This is anomalous diffusion of activity. What else? And here in the velocity field, for this specific time, you observe that there is velocity only for this active region, as would be expected. In the passive region, we don't see the velocity 0. Okay, so how to analyze the dispersion of activity? we can measure the mean square displacement of this activity field of the field zeta using the second moment of this field. And if you plot the logarithm of this mean square displacement as a function of the logarithm of time, we observe that it evolves according to a power law after a transient regime, which is subdiffusive. So we can measure the slope of these curves, which are for different activities, and plot the slope against the activity. What we see is that above a certain activity, this slope tends to a certain value, which taking the average, it is 0.75. So if this slope was 1, we would say that the motion is diffusive. But this is below 1, this is subdiffusive. And then how to study the dispersion of this activity? We can measure an analogous coefficient, analogous to the diffusion coefficient, but assuming already a power law of 0.75. So if you measure this subdiffusion coefficient and plot it against the activity, we see that this coefficient, it increases with activity. So the more active the system is, the more it will disperse the activity, as would be expected. What is not intuitive is that it is subdiffusive. Another effect that we investigated is the dependence of this subdiffusion coefficient with the shape of the particles. And our motivation comes from the literature in biomedicine. And it's known that the bacteria, they are able to change their shape when they are swarming. But it's not known why they change their shapes. So here we observe that on the top, they are more elongated, and here they are more circular or more spherical. The same kind of bacteria in the same domain for different times. And in another study, the authors were able to change the shape of the bacteria in the laboratory and using chemical substances. And what they observe is that for a certain aspect ratio, there is a maximum vorticity, an average vorticity in the system. And we know that the higher the vorticity, the higher is the dispersion of a certain solute in the domain. So this raises a question. If we can ask if the bacteria change their shapes to spread better the nutrients in the domains. It would be desirable to let the nutrients reach all the portions of the colonies. So in our simulations, we have measured this the subdiffusion coefficient against the aligning parameter, which is related to the shape of the particles. And here it's plotted for 2 different activities. And what we observe is that it's non-monotonic with this aligning parameter. So there is a maximum value for the dispersion, for the subdiffusion coefficient, for a certain value of aligning parameter. This suggests that there is an optimal shape for the dispersion of nutrients, which would be guessed from these experiments. Right? So to conclude, we have presented a model for the dispersion of nutrients in active kinematics, and we observed that this motion is actually subdiffusive due to the defects entering and leaving the active domain. And we also observed that this subdiffusion coefficient increases with the activity, and it is non-monotonic with the aligning parameter, which is related to the shape. This has an interesting conclusion that there is an optimal shape for the dispersion of nutrients in bacterial colonies. And this study is not published yet, but let here some two previous publications on the same topic. This one was on the special issue of this conference from the last year. And we thank you all for your attention. I'm ready to answer your questions if there are any. Thank you.
Thank you so much, Rodrigo, for your presentation and questions. We have time, so if you have questions. No one? Okay, so I think we can, if there are no questions, we can conclude this session. Thank you again to all the presenters, and I think we will update at 3 p.m. If I don't go wrong, I don't have the program here, but yes, yes, perfect. And so thank you again to everyone, and see you later. Okay, now Marco, se ci sei,
dimmi.
Concludo, tanto sono io l'organizzatore, concludo
la registrazione in basso.